Hello, Lindenwood Stat students. Coming at you from my basement. I'm a little bit too old to be living in a basement, but anyway, hope you're all doing well out there. And try to enjoy yourself this weekend. I think I'm going to barbecue. Anyway, let's get on with it here. We're in section 9.2. We're going to do basically the same thing that we did in section 9.1 for population proportions with population means now. That means we're going to take a sample, find the average of something associated with that sample, average height, average salary, and so on. And we're going to use that average from our sample as an estimate of the average for the population. Then we're going to construct some interval around that where we're a certain percentage confident that the mean for the population is somewhere in that interval. So it's the same kind of language. But it's going to be a little bit more complicated because there's going to be two different situations. We're going to be talking about Z intervals, and I'll sometimes refer to this as Z statistics or Z stats, and T intervals. And we need to be able to distinguish which one of those we're using for a particular problem. And there's a very surefire way to do that, and I'll tell you what that is. We're going to both methods are explained in detail later in this section, okay, but we'll begin with a short summary of when you would use each type of interval. Okay, if you know the standard deviation of the population, some of you might have wondered about this already. We've had many problems where we're given the standard deviation of the population and we need it in order to calculate certain things. Well, if you don't know the mean, you're probably not going to know the standard deviation either. So it's very uncommon that you know the standard deviation of the population. Sometimes people just know it if they're doing long-term studies, they know it from past experience, but it's still rare. In any case, if we are given the standard deviation of the population, normally not known, then you would use Z statistics or a Z interval. And in real life, that's going to be very uncommon. But in this class, it'll be 50-50 because we're covering both of them. If you don't know the standard deviation of the population, which is common, then you're going to approximate the standard deviation of the population with the standard deviation of your sample. And then we're going to use something called a T interval or T statistics. Okay, so we got to get that down from the start, that we're going to have to do two different things. That's going to make it twice as complicated. All right, let's see what happens here. Constructing a Z interval for a population mean. All right, what do we do? We have to assume that we're given in the problem the standard deviation of the population. The spread, we don't know the average of the population in this case, and we're supposing that we know the standard deviation. You can see that doesn't make much sense, but we'll think about it anyway. The population, if we know that the population is normal, or if we're working with a large sample, and remember the rule of thumb is that means n is greater than 30. If either of these criteria are satisfied, then the sampling distribution is approximately normal. Well, those criteria are always going to be satisfied in this class because we're working on problems where we assume that they're satisfied. But we might be asked to justify it. All right. Here's what I said. Draw a sample size and calculate the sample mean. Okay, that's X bar. We're all familiar with that. This is the point estimate for the population mean. But it's not going to be equal to the population mean because it's just a sample. Since we know the true population standard deviation, then we can calculate the standard error by taking sigma divided by the square root of n. This is the central limit theorem, that the samples, the range of samples that you can get, I'm just going to give this in words. As I mentioned, it's a mathematical theorem. It's not very difficult to prove as mathematical theorems go, but we're not doing that. But basically what it says is that the spread of averages you get out of samples is not as spread out as the whole population is, because you're averaging out some of the variability in the population by taking samples. Okay, so you select the confidence level beta. We're used to that now because we had to do it last section. That's 90, 95, or 99% usually. And that's going to alter our calculations with that Z factor. Okay, then the margin of error is, notice that they're using Z here. Yeah. Z statistics. So this is Z stats. The standard deviation of the samples is sigma over the square root of n. The error is that Z number. I think for 90, I'm starting to remember them now because we've used them so often. I think for 90% it's 1.645, and for 95% it's 1.96. I don't have that little table in front of me, but I think that's right. We'll use those numbers for today. So the 90, 95, or 99% confidence interval is given by somewhere between X bar, which is right in the middle of the interval, and plus epsilon and minus epsilon on either side of it. So that's what a confidence interval is for a mean. Okay, an interval constructed in this way. So in words, an interval constructed in this way will have a 90, 95, or 99% chance of containing the true population mean. Okay, so it's very much a similar idea to what we were doing in the last section. So let's do this example. Assume we are interested in estimating the population mean salary, we'll say, call that mu, of a certain city. Suppose it is known that the salaries have a population standard deviation of. This problem is missing something very, very important. You're being given the standard deviation of the population, which is sigma. We're learning all these new Greek letters this semester. Oh, it's fun. Okay, so it's going to be given in the problem as I looked up on the notes, and this is supposed to say sigma equals $2,500. And you would say, well, if you don't know the mean salary, you probably don't know the standard deviation either. That's what's unrealistic about this problem. But you have to be given this. You have to be given, if you're given this in the problem, the standard deviation of the population, then you're going to use Z statistics. That's the giveaway. If you're not given that population standard deviation in the problem, if you're not given it, then it's T statistics. Okay, so let's get rid of Z statistics right now. Since the sample is large, this is bigger than 30, 100 people, it tells us that the distribution of means is approximately normal with the same mean as the population. Okay, so sigma x bar is equal to the standard deviation of the population divided by the square root of n. That's the central limit theorem result. And you see, you can't calculate this unless you know the standard deviation of the population. That is the Z statistics giveaway. So I got to take $2,500, that's given in the problem, divided by the square root of 100. Oh, that's nice. That's 10. So that's equal to $250. You know, if I take samples of 100 people, their averages are not going to vary as widely as the individuals in the population. And that's the essence of the central limit theorem, and that's what makes statistics possible. Okay, so I found sigma x bar. Now what am I going to do? Here's B. Assume we wish to construct a 95% confidence interval. Find the critical value of Z. I believe that is 1.96. Once again, I don't have that table in front of me, so we're just going to go with it. Okay, now we're going to calculate the margin of error. That's equal to, that's called epsilon, was last section. It is this section also. Z times sigma over the square root of n, which is equal to 1.96 times, 250. Okay. Well, let's figure out what that is. Where's my calculator? Here it is. 1.96 times 250. $490. Okay, assume that the mean of the sample we collect is $40,000. Then construct the confidence interval. Okay, so we're going to 490. So the confidence interval is going to go between 40,000 minus 490. 40,000 minus 490. Up to 40,000 plus 490. Okay, and that's, we can do this. That's 39,510, I guess. And this would be 40,490. I think. Okay, oops, yeah. Okay, here is a way to do this on a calculator. That reminds me, I've posted my first try of a calculator crib sheet that we might be using in the near future. So if you want to, you can take a look at it. I'm open to suggestions of things to be added to it. It's already 4 pages long, for Christ's sake. So you can take a look at it. It's posted on Canvas. All right. So let's see what the calculator gives us. Here are the steps to use the calculator. So press the stat key. All right. Arrow over to tests. Scroll down to number 7, Z interval. See, we're using Z statistics. Oh, look, here's a Z test and a T test. Oh, very good. So the calculator is using the same jargon we are. always good. So I'm going to choose number 7. And then it says either data or stats. I want to, if stats is not highlighted, select it and press enter. Okay, now see they're asking for sigma. So the calculator knows that if you're using z-stats, you've got to know what sigma is. You've got to be given that in the problem. And that was 2,500. Once again, if you have an older version of this calculator, you might have to put the same data in, separated by commas after it. It may not be prompting you. What was X bar? That was 40,000. 40,000. And what was N? That was 100. And what was my confidence level? That was 0.95, 95% confident. And that's already in there, so now I'm going to press calculate. So there it is. 39,510 to 40,490. That is indeed what we got. So that's good. All right. A researcher is studying the height of men. Oops, let's get rid of the calculator here. A researcher is studying the height of men with a certain medical condition. She draws a sample of 100 men and finds their mean height to be 68.5 inches, X bar. Assume the sample that the standard deviation for the population of men with the condition is the same as that for the general population, 2.8. Here is the important sentence. We are being given the standard deviation of the population. Immediately that means we're going to use z-statistics, and we're going to use that z interval that we just did. Find a 90% confidence interval. Okay, I want to find a range of values where I'd be 90% sure that the not sure, I don't like that, it's not a good word. 90% confident that the mean of the population is somewhere in that interval. Okay, so 68.5 is going to be the center of the interval. And let's use the calculator. See if we can remember how to do it. Get my calculator. Okay. What was it? Stat. Tests. 7. Z interval. Stats is highlighted. The standard deviation is from the problem, and it's 2.8. The mean is the X bar is 68.5. And N is 100 again. I only want to be 90% confident in this particular example. So I go down here and then press calculate. And I get it's 68.039. There's the center of the interval, 68.5, which is this right here, of course. And the other end of the interval is 68.961. If I want to know the error here, what do I have to do? I have to take the right-hand side, subtract off the mean, and I'll get it. So it'd be 68.961 minus 68.5. I can also take the difference between the two endpoints and divide by 2. 68.5. So if I wanted to find the standard error, I'd take 68.961 minus 68.5. 0.461. not the error, not the standard error, the error, what is that called? Margin of error. Okay, anyway, it's epsilon. Find a 95% confident. If you want to be 95% confident, then it's going to be a wider interval. So let's use a calculator for that. Stat, arrow over to test, down to 7. Everything's the same here, except I want to be 95% confident. Calculate. And indeed, I get a bigger interval. It's got a lower left-hand point, 67.951, and an upper of a bigger number for the upper too, 69.049. And once again, the margin of error is either this minus 68.5 or this minus this divided by 2. Okay. Good. An additional problem. A researcher is studying the height of men with a certain medical condition. She draws a sample of 105. Find a 90% confidence interval for the population mean, mu, of men with this medical condition. All right. I already did that. Didn't I? Yep, there it is right there. Probably still on my calculator somewhere. Oh, no, I didn't answer all the questions here. Find a 99%. Find a 99%. Well, that's even going to be a bigger interval. And then find the margin of error for each of the intervals above. Okay. Get my calculator back. I'll do second enter. No. How about second enter? No. How about stat? How about tests? How about 7? Everything's the same here except I want 99%. Even a bigger interval. It's 67.779 up to 69.221. As I said, another way to find the margin of error is to just subtract these two, 69.049 minus 67.95, and divide it by 2. Because the interval is twice as long as the standard of error, margin of error. I'll let you do that on calculator. Same there, same there. Now, what is this problem? Additional problem. Find a 90 round. I already did that. Determine the margin of error. Round to 1 decimal. I already did that. What's the smallest sample size that would produce a confidence interval for mu with a margin error epsilon equal to part B? Okay. Huh. See if this problem is missing something. another formula. I didn't see it back there, so maybe it didn't make it in the notes. I would say that n, the smallest sample size that would give us, I need to do a little bit of algebra in my head here. Let's go back and look at this formula. If I want to calculate n for a certain epsilon, I think it would be z, the critical z value, times standard deviation of the population divided by the margin of error squared. Let me see if I can find that on a formula sheet. Looking at a formula sheet here. Yeah, that is correct. All right, well, let's just do this. Find a 90% confidence interval. This is all the same stuff. 100 men, 68.5 for the sample. Sigma's 2.8. This is all the same stuff. So let's turn it on. We're supposed to find a 90% confidence interval. So stat, tests, 7. Everything's the same except I will only need to be 90% confident. And do it. There it is. The margin of error is equal to 68.961, 68.961 minus 68.039 divided by 2. Okay, so 68.961, 68.961 minus 68.039. Make sure you press enter here, not just directly divide by 2, otherwise it's just going to divide that second number by 2. Then do divided by 2 after you subtract them, and you get 0.461. Round to the nearest whole number. Oh, okay. Well, let's see. 68. Round to the nearest whole number. Well, I guess that's what we're supposed to do here. All right, so let's round these to the lower limit is going to round to the nearest whole number is 68. The upper limit is rounded to the nearest whole number is 69. Right, and then the margin of error is equal to 69 minus 68 over 2, which is equal to 0.5, round to one decimal number. Okay, so if I wanted a margin of error of 0.5, how many n's would I need? I bet it's going to be around 100. Um, so let's do it. For 90%, the critical value of z is 1.6. Oh, I'm gonna have to square this whole thing, so let's get a parentheses in there. I think it's 1.645. And then I'm going to have to multiply by sigma, which is in the problem. So times 2.8. And then I got to divide by 0.5. And then I'm going to square it. Uh, 84. So I'd have to take 85 people. 100 would be better. All right. Let's see what the students' T distribution. Okay, this is going to be the second situation where we don't know the standard deviation of the population, which is going to be much more common situation. You know, when I was first learned about students' T distribution, I thought, oh, this must be based on something to do with students, because, you know, I was a student at the time, so I thought, oh. That's a guy's name. Anyway, we'll do that on Monday. Have a good weekend.